Hello and welcome to a presentation from Spirent and Calnex Solutions about the impact of latency and loss in a network on throughput. This is a presentation that looks at some of the challenges, particularly in moving or migrating to 40, 100 gig high-speed Ethernet networks. The presentation looks at the problems that latency causes in the network, but before we do that, let's ask ourselves the question, why do we get latency and loss in a network? Latency is primarily caused by a propagation delay, switching routing, as well as buffering and queuing within those routers. Today, a lot of the internet traffic, for example, Netflix, YouTube, and Amazon video traffic, is carried by TCP protocol. In fact, estimates that it's between 80 and 90% of traffic on the internet is running at TCP. One of the problems with TCP is that throughput of data traffic for TCP-based traffic is heavily impacted by latency because it is a connection-oriented protocol. The reason for this is that TCP waits for an acknowledgement before sending next packet. That's obviously affected by delay if it has to wait for the acknowledgement. If the packets are lost or not received within the time limit, retransmission happens, and that's all obviously impacted by latency. What this presentation will look at is why this might be an even bigger issue when moving to 40 and 100 gigs, and therefore it needs to be checked in the lab prior to this deployment. We need to simulate the network in the lab prior to any deployment. We need to add delay and other impairments to test the impact on user experience, in other words, the throughput of data or service. We also need to error and lose the packets. So ordinarily, we could use large drums of fiber to simulate this network in long distances and the corruptions. However, this has a big challenge. Using drums of fiber has a number of significant challenges. Obviously, too big and large and heavy. For millisecond of delay, you need 200 kilometers of fiber. You will see later on that networks can actually introduce even 100 gig, tens of milliseconds of delay to a packet. Tens of milliseconds of delay would, for example, from LA to New York, just the fiber delay alone, where 22.5 milliseconds would require 22.5 drums of 200 kilometer fiber. Obviously, that's expensive from a number of reasons, to buy the fiber itself, but also the lab space for storing the equipment. That's going to be extremely expensive. There is a cost to amplifiers that are needed on the link, and therefore the setup and the operation costs could easily hit $1 million in year one alone. So it's obviously not a very practical solution to emulate these network effects. The bigger challenge, obviously, or as big a challenge, is the lack of control. If you want to run a service or a test and throughput is impacted or test fails, you want to then control the amount of delay, and that can't really be done easily using real fiber drums. Obviously, as I mentioned before, you need amplifiers to go those differences, and these things can cost a lot of money. So the cost and the impracticality of doing it this way, as well as the lack of control in being able to turn up or down a delay, means that this is not a practical solution to emulate delays to test the impact on throughput. I want to look at a little bit more detail before coming on to a proposed solution of the problem of latency. So let's ask again, what causes it, where does it come from, and why is it such an issue? So we asked the question, what causes network latency? So network latency is caused by propagation delay, the latency caused by the routers or switches, and the queuing within these devices themselves. So the propagation delay could be anything up to let's say an international link of 5,000 kilometers, that's 26 milliseconds of delay. If in that link we had a router every 800 kilometers, just as a number, that would add another 1.5 milliseconds, 1.4 milliseconds. And then obviously each router can add microseconds or milliseconds of latency to that packet. So you can see very quickly that tens of milliseconds of delay is reasonable within an IP packet traversing any amount of distance or any number of hops. The challenge with that kind of latency is that it does matter, as we've discussed before, for a connection-oriented protocol like TCP. The reason is TCP waits on the acknowledgement to establish the connection. If packets are missing or don't arrive within time, it uses the acknowledge to request a retransmission. it uses a windowing technique, which we'll look at in a little bit more detail, on waiting for the acknowledgement to slowly increase the transmission rate to match the available bandwidth. In other words, it tunes up the data transmission rate by testing where the limits are of that transmission. And this windowing technique is what impacts its bandwidth. Again, we'll look at this in more detail later on, because the throughput, this is the fundamental reason why throughput is affected by latency in that network. So if we now look at the windowing technique that we talked about in a bit more detail, the windowing is the TCP slow start protocol. And slow start, quite simply, means I send up a packet, I wait for the acknowledgement, and then if it comes back successfully within the allowed window, I then double the transmission rate. So I send 2 packets, wait for both acknowledgements, and again, if that's successful, I double it again to 4 packets. So basically, the slow start process allows the packet rates to be doubled. And of course, once that transmission bandwidth is exceeded, or there's too much latency in the ACKs coming back, then TCP decides that I've now exceeded the allowable or the available bandwidth, and then it then reduces the transmission rate. In fact, when a packet is lost, whether it's congestion or takes too long, the sending rate is actually halved. And then when slow start kicks in again, it doesn't double the rate, but increases it more slowly. So for example, it goes from 1, 2, 4, 8, 16, and so on, and it goes up to a certain level, and then if it hits a problem, it halves it, and then tries to detect the optimal point by slowly increasing the packet rate. The whole process is obviously very sensitive to the delay through the network, because if the acknowledgement doesn't come back in time or is lost, then obviously TCP kicks in and controls the amount of data going through. If we look at some real-world examples of how this impacts, you can see that with just a 30 millisecond round-trip delay, again, a quite reasonable number in transmission, and you can see that windowing or TCP windowing and the impact it has on the throughput. So this is a graph of throughput, and you can see the graph zigzagging up and down. And this is interesting because obviously TCP kicks in, it increases the throughput. When it hits the limit, windowing kicks in. And obviously the data is constantly halted during these downslopes because the window size is full, and wait for the sending node waiting for the acknowledgement to come back. Now, one of the things to bear in mind is that this windowing technique, or the window becoming full, and then the data going out not being sent, could become even more critical at higher speeds, because the same window size obviously fills up a lot quicker with data. So you can exceed, if you don't set up the network or equipment correctly, you could exceed the TCP windowing size at much quicker or much lower latencies. And on the right, you see for a satellite link with 250 milliseconds of round-trip delay, TCP throughput can fall pretty significantly. Now, with high-speed networks and 40-100 gig networks, obviously latency or high amounts of latency isn't the issue. You're not going to see very high latencies. You're going to see latencies more aligned to the left side of the network. But the point is that even with these latencies, the impact could be much greater because TCP windows could fill up quicker. And the TCP slow start and the bandwidth management or throughput management protocol kicks in. And some other illustrations here of the combination of both round-trip delay or latency and a packet loss. You can see that both round-trip delay and latency and packet loss have a pretty significant impact to the throughput of data in a network. And even just 3% packet loss, you can see can significantly impact the throughput on a network. In other words, anything that's running on TCP, whether it's running 1 on 10 gig, but more importantly at 40-100 gig, needs to be verified in the lab for the impact of packet loss and latency. Not a lot of loss, not a lot of latency, but we do need to emulate this and find out exactly what the impact is on this, on the TCP throughput. So in summary, latency, which is caused by the propagation of across the fiber, across great distances, routing equipment, as well as the buffering and queuing within the equipment, causes latency in a network. The fact is that streaming video and a vast majority of internet traffic today is carried via TCP. which relies on a connection via handshake and acknowledgement process. And therefore, throughput is greatly affected by latency and loss, because retransmission as well as a stepping down of the throughput occurs because of the TCP protocol. So, in other words, and we've also talked about the problem of using fiber drums to emulate these delays. It's too big, too expensive, and you can't really control the delay. And therefore, you can use products like the Atero family from Spirent and Calnex to emulate very accurately delay critical data, for example, for financial services or video traffic. It's repeatable, precise, and controllable. You can emulate network effects like latency, loss, and errored packets using these products in a lab environment. Why would you do that? Well, you want to test how, for example, an enterprise or a data center will perform. It's really an IT-based pre-deployment test where you can test the impact of latency or loss. And this is, again, quite useful and interesting when a 1 or 10 gig network is migrating to 40 or 100, or even a 40 gig network is migrating to 100 gig, because you want to see what the impact is on the TCP windowing of these different delays in that network. And obviously, how will the network elements themselves perform? So the verification of a network equipment or a piece of data center equipment can be how is that affected by real network latency and loss? You can emulate that accurately in the network. And then obviously the ultimate goal here is what is the customer QoE impact for things like video going to be over the real network. So the test setup that we use is a traffic or test packet generator to go through the system or the network under test, and the Atero product from Spirent to emulate the network impairments. So, for example, those delays that you have. So the value really is to allow these systems and services under test to be tested under real network conditions, and importantly, for the impact of TCP, so impact of latency and loss to the TCP protocol, and their subsequent impact to the throughput, and then their subsequent impact to the user experience can be fully established and analyzed. And importantly, the margins of operations or the limits of operations can be established for that service on that network. That is a presentation about the challenges that latency introduces to TCP protocol and therefore the impact on the user traffic. It also talks about the Atero family of products, which comprises a 110 gig platform, a 40 100 gig platform, and also now a virtual solution for emulating network latency, loss, and other effects. Thank you very much.